let's get started. So, just a second here. Okay. So, yesterday we started our discussion of the theory of angular momentum with the simple example of translation. I say simple, even though it has all the right ingredients that we need for our study of angular momentum. But since the generator of translations is just ddx, it makes things a little simpler as opposed to rotations. But the reason we are starting with this example is because it gives us all the basic structure that we will need to understand angular momentum. So even if you get bogged down with certain mathematical complexities in terms of angular momentum, please understand that you already know everything about the basic structure of how these transformations and these unitary operators look like and how these transformations act in the Hilbert space and things like that. So that's the reason why we are taking this route. Okay, so let's quickly recap what we did. So the essential points of yesterday was that symmetry operations are realized by unitary operators in the Hilbert space of the quantum mechanical system. Okay, so for example, in the case of translations, there is an operator that realizes this translation on the states of the system. And this operator, I can always construct an infinitesimal operator because this is a continuous transformation. And this infinitesimal operator I called T yesterday of translation. And then we wrote T in a very specific form. We wrote T as, where did we write it? So 1 plus I epsilon over h bar times G. And this G is a very, very important object in quantum mechanics. And G is called the generator. Okay, in this case, we are generating translations. So G is a generator of translations. And we later found out that this generator is nothing but the momentum operator. So if we demand T to be a unitary operator, we necessarily have that G is a Hermitian operator. Okay, so this is very important to understand. Now we can go ahead and construct G, and this is why I said translations are slightly simpler, because in the case of rotations, we would find that this generator actually depends on the dimension of the representation, something that I will explain as we go along. But in the case of translation, we can construct this G ab initio, and we found that G is nothing but the momentum operator P. Okay, and then we wrote down the final form of the infinitesimal translation operator in quantum mechanics, and this is nothing but I minus I epsilon over h bar times P. Okay, now somebody asked me yesterday when I wrote down this expression, a very important question. If you write the translation operator as epsilon times an operator, epsilon squared times another operator, and so on and so forth, if you want to construct a finite translation operator, not just moving it by 1/15th of a nanometer, but if you want to move it by 1 meter or something like that, we have to construct a finite translation operator. And wouldn't you need an infinite number of operators to understand what this is? And today we will answer that question, and you will actually find that we actually don't. The way we will construct a finite translation operator is by piecing together many infinitesimal operators, and all we need to know is what is the generator of the infinitesimal translation. That is the power of this approach. Okay. All right. So let us continue from where we left off. And today I want to start the discussion by talking about translation invariance, or the notion of symmetry. Okay. Now, by itself, understanding the translation operator is important, but it becomes even more important when you have a physical system that is invariant under translations. Okay. So, for example, a periodic potential is a very standard example in physics of something that is invariant under translation. So, remember that the Hamiltonian of a system is kinetic energy plus potential energy. The kinetic energy term, which is p squared over 2, is always invariant under translations, because ddx doesn't care if it is x or x plus a. So it is the potential energy term that is important when you understand symmetries of a system. And if you have a potential energy term that is translation invariant, the system is said to have a symmetry under translation. And this, as you know by now, has important consequences. So how is this symmetry realized? So in the case of translation, we have what is called the translation invariance. Okay. So how is this symmetry realized? As you must have seen in your classical mechanics course, when I say a classical mechanical system is translationally invariant, I simply mean that the Hamiltonian does not change under the translation, right? So that is a very simple statement, and you would actually see that the statement in quantum mechanics is also sort of similar. So in quantum mechanics, what do? We start with a set of states psi, and after the translation operator has done its job, these states move to a different set of states psi epsilon, which is given by t times psi. Yeah. Now, the statement of symmetry in quantum mechanics is simply that the expectation value of the Hamiltonian operator in the states psi and the transformed states psi epsilon is exactly the same thing. If you want translation to be a symmetry, then you demand that this guy is equal to this guy. Okay. Now, we don't usually state it in this form. There is a much cleaner way in which you can express this. There is two equivalent ways you can express this. To understand what that is, simply plug in the definition of psi epsilon on the right-hand side of this equation. So, psi h psi equals, psi epsilon is just t times psi. So, this is psi t dagger h t epsilon psi. Okay. So on the left-hand side, we have an operator h sandwiched between psi and psi. And on the right-hand side, we have an operator t dagger ht sandwiched between psi and psi. And the only way these two matrix elements are equal is if the operators that are sandwiched between the identical states are also equal. So this tells us that an equivalent way to formulate the existence of symmetry in a quantum mechanical system in this case is by claiming that the transformed Hamiltonian is formally identical to the original Hamiltonian. So this is the statement of symmetry in quantum mechanics. So this is important, so I'll box it. Okay. So if there is any questions, stop and ask me.
Hello, sir.
Yes.
Sir, when you were talking about classical mechanics, you were saying that in the translation invariance, the Hamiltonian should be invariant. But sir, shouldn't be the Lagrangian should be invariant instead of Hamiltonian? Because if I took the time translation, then should be the Hamiltonian invariant. But if I took the space translation, then shouldn't be the Lagrangian should invariant?
So you can you can formulate quantum mechanics in both the Lagrangian picture and the Hamiltonian picture, right? They are related by a Legendre transformation. So
Yes,
if you look at the Lagrangian picture, where Lagrangian is t minus v in classical mechanics, then you can also talk about symmetries of the Lagrangian, and then what you say is true. So for example, whenever there is a symmetry in a classical mechanical system, in the Lagrangian picture of looking at it, you always identify a corresponding variable that is cyclic, right?
Yes, sir.
And if so, what does this mean? This means that the Lagrangian doesn't explicitly depend on this variable. And if we call this variable q, then as long as you have you identify a set of generalized coordinates and you look at the Lagrangian and see which one of these generalized coordinates the Lagrangian has no explicit dependence on, right? So if there is one generalized coordinate q3 upon which the Lagrangian doesn't depend, which is dl dq3 equal to 0, then there is a corresponding canonical momentum that is conserved. So this is how you formulate the symmetry in the Lagrangian picture. In the Hamiltonian picture, it is sort of the same. You simply formulate it in terms of the Poisson brackets, right?
Yes,
so
sir.
you say that the Poisson bracket of the generator of the translation of the transformation with the Hamiltonian is 0, right?
Yes, sir.
So does this ring a bell? You actually claim this. Yeah?
Yes, sir.
So in quantum mechanics, so this is what I'll come to. We have something very similar to the Hamiltonian picture. So this is why the correspondence with classical mechanics is often easier in the Hamiltonian picture than in the Lagrangian picture. But your point is well taken. You can formulate the symmetries in both the Lagrangian and the Hamiltonian picture, but I will use the Hamiltonian picture because in quantum mechanics, you start with the Hamiltonian.
Okay, sir.
Okay. So to complete this discussion for those who are interested, it's actually interesting how you move from, for example, a relativistic theory, a non-relativistic theory to a relativistic theory. Okay, so in a manifestly relativistic theory, it is Hamiltonian is actually a derived concept. You don't start with the Hamiltonian of a system. You start with what is called the Lagrangian density. Okay, in a relativistic theory, the reason you do this is because you can define what is called a Lagrangian density, and this Lagrangian density, this object integral S d4x, d4 and not d3, because in a relativistic theory, space and time are treated on an equal footing. And the Lagrangian density is what is actually a scalar under what are called Lorentz transformations. The Hamiltonian actually transforms under Lorentz transformations as the time component of a 4-vector. So you don't actually start with Hamiltonians in that sense.
Sir, here you are talking about classical field theory, right?
No, this is about either a classical field theory or a quantum field theory. It doesn't matter, but I'm talking about quantum field theory in general.
Okay, sir.
Oh, anyway, so I will continue. So can everybody please self-mute because there is a lot of background noise. Anyway, I think some people often joke that this is the difference between particle physics and condensed matter physics, because particle physics start with Lagrangians and condensed matter physics start with Hamiltonians. Anyway, so moving on to our formulation of symmetry in single particle quantum mechanics. Now I can use the notion of generators to formulate the exact same symmetry in a different way that is more in line with what you do in classical mechanics. So you take the form of T that we discussed yesterday in class, which is the boxed equation on the page above. So I will write this as I minus I epsilon over h bar times the momentum operator and plug this into the second box. So what do you have? Momentum is a Hermitian operator. So T dagger would be I plus I epsilon over h bar times the momentum operator times the Hamiltonian I minus I epsilon over h bar times the momentum operator. It has to be equal to the Hamiltonian. Okay. Now notice that since it's an infinitesimal transformation, I'm only restricting myself to order epsilon and neglecting epsilon square and all the other terms. So evaluate the left-hand side. The first term is just h, right? And you have to be very careful with the order. So p and h may commute, may not commute. You have to see what the consequences are. The second term would be the p multiplying the h multiplying the I, right? Excuse me. So that would be plus I epsilon over h bar p times h. The third term would be p multiplying h multiplying the second p, but that will be a term proportional to epsilon squared. So I will safely neglect it because I'm only working to order epsilon. The only other term would be I multiplying h multiplying minus I epsilon over h bar p. So that would be minus I epsilon over h bar, this time h times p. Okay, and plus terms of order epsilon squared that I will neglect. And this has to be equal to h on the right. Okay, so if you work this out in the language of generators, if I claim that the translation is a symmetry of the quantum mechanical system, this necessarily means that the commutator of h and the generator of the translations is 0. This is an equivalent way of stating the exact same symmetry. Okay, so this is for people who remember the classical mechanics. This in the classical mechanics, this is a Poisson bracket. In quantum mechanics, this is a commutator. So there is multiple ways of stating this. We can state that the expectation values of the Hamiltonian operator in the states before and after transformation is the same. That is a little cumbersome. So you go to the first box, which is a statement about operators. So for any operator, this is how the translation operator affects the operator. T dagger, O, T. And the way to formulate the symmetry of the quantum mechanical system is to claim that the Hamiltonian is unchanged under the transformation. So the transformed Hamiltonian is the same as the original Hamiltonian in terms of the T operator. But in terms of the generator, it also means that the Hamiltonian commutes with the generator of the translation. So remember that whatever I have said here is completely general for any transformation. So suppose if I have rotations, and suppose if there is a rotation R that is represented as some kind of a unitary operator in the Hilbert space such that psi R is U of R times psi, that if you have a quantum mechanical system in which rotations are a symmetry, just like the hydrogen atom problem, then you would have that U dagger R H U of R equals H. Okay, and whatever the generator of the rotation is, let's call it some J. You can also claim that the Hamiltonian commutes the generator of the rotations. Okay, and so on and so forth for any continuous transformation. So for any continuous transformation, you identify what the generators are, and if this continuous transformation is a symmetry of the quantum mechanical system, then the statement is that the Hamiltonian commutes with the generator of that particular transformation we are talking about. Okay. So this is a statement of symmetry. And why is symmetry important? Well, symmetry is important because it simplifies our problem, right? So we simply look for common eigenstates of the Hamiltonian and the corresponding generator of the symmetry. And this is exactly what we did in the hydrogen atom problem. We looked for simultaneous eigenfunctions of the Hamiltonian at L square and LC, right? So you collect as many operators that commute with the Hamiltonian. In other words, you look at the full symmetry group of the Hamiltonian, and then you look for simultaneous eigenfunctions of all these operators. And this has the advantage that once you have all the eigenfunctions, the action of these eigenfunctions on a whole bunch of operators is extremely simple. Okay, in other words, we simultaneously diagonalize the Hamiltonian with all the symmetry generators that commute with the Hamiltonian. Okay. So the final piece that we have to address before we move on to rotations is what is a finite translation. So let's talk about the finite translation. Okay, what is a finite translation? Well, in many instances, we are interested in moving the object not by a very, very small amount, but by a finite amount, say A. So I'm interested in asking the question, what is the operator that corresponds to a translation by a finite amount A? Okay, the way I will answer this question is by saying that, look, since it is a continuous transformation, I can always get to a finite translation by doing a whole bunch of infinitesimal transformations. So if I'm originally over here, I'll go 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 over here, and I'll keep going. Okay, I'll keep going until finally I get to where I want. Okay, now each of these translations is by an amount epsilon. Okay, but the final translation is putting together a whole bunch of infinitesimal transformations is A. So let us say that I do this procedure n times, which means if somebody wants me to go from x is equal to 0 to x is equal to 5, I will take about 15 billion steps and go from x is equal to 0 to x is equal to 5. Okay, that is exactly what I'm doing, which means that I'm doing it, and let us say do it in n steps such that epsilon equals A over n. Okay, So I want to do it in the limit that n goes to infinity or epsilon goes to 0. So this is how I will realize a finite translation. So a finite translation is simply T of A is simply T of epsilon n times in the limit n goes to infinity. Okay. And epsilon, as you say, is the finite translation operator divided by n, which is the number of times you're doing it. So this is limit n goes to infinity, T of A over n done n times. Okay. So if there's any questions, please stop me and ask. And this is all you need to understand what a finite translation operator is. So this tells you what the power of this approach is, because everything that you need to know about a finite translation, you can guess by already writing down the infinitesimal generator. So the generator is very, very crucial object in the case of continuous transformations, because once you nail down what the generator is, you know everything about the transformation. So let us work this out. Let us see what this object is. So T of A over n is limit n goes to infinity. What is this object? This is identity minus I epsilon, but epsilon is now A over n. So A over n h bar P taken n times. Okay. And you might know what this object is if you take the limit n goes to infinity, but if you don't know what this is, we can easily evaluate this. So aside, let's evaluate this quantity in case you've not seen this before. Evaluate, let us say limit n goes to infinity. This is of the form 1 minus ax over n to the n, right? So in our case, x is an operator, but it doesn't matter. Once you evaluate this, you can straightforwardly generalize this to the previous one also. So what is this? Let us call this object, limit n goes to infinity, 1 minus ax over n to the power n as some object q. Okay. Now take the log on both sides. That's the simplest way to do this. So n log 1 minus ax over n is just log q. And now since n is very, very large, I can expand this logarithm. Okay. But when I expand this logarithm, I should also, so somebody is asking, why is t to the n and not nt? So no, I actually need to translate it to a finite amount, right? So suppose if I do it, so okay, this is a good question. So let us see what it is that I'm doing, right? So I'm moving from place to place, right? So this is actually important because this tells you how the operators act. So and when you say you're doing NT, you're actually meaning that I'm adding the operators, right? So operators do not add. So when I say that I'm moving from 0 to A in, let us say, 20,000 steps or something like that, I'm not claiming that T of A is T of epsilon plus T of epsilon plus T of epsilon and so on and so forth. Okay, this is not what I'm doing. Why? Because so that acted on some object, right? So what is n times T of epsilon acting on some state psi? Okay, and evaluate what this object is. So this would be T of epsilon acting on state psi is just state epsilon n, sorry, this is n times psi e. Okay, now this is not the translated state for a finite translation. This is just n times the translated state by epsilon, which means all the vectors in my Hilbert space have transformed from psi to some number times psi. And this number I can always absorb in the normalization and claim that this is exactly the same vector. So I'm not actually doing anything. Okay, so operators do not add like this. Okay, so let's finish this derivation. So when I do this expansion of the logarithm, I should also bear in mind that there is an n outside, and n is a very large number. So log of, excuse me, log of 1 minus x is, what is this? This is like minus x square over 2 and things like that, right? Now, what is the leading term in this expansion? The leading term in this expansion is x. In this case is ax over n, and the n cancel for the leading term. The leading term is n independent. If I look at the first order term, it will be a square x square over n square, and this multiplies the n outside, and the second term is 1 over n. And since n is very large, I can safely neglect the second order terms and simply write the first order term, which is n independent. So this expansion would simply be equal to n times minus ax over n equals log q, which tells me that q is just e to the minus ax. Okay. So that's a very simple way of understanding what the finite translation is. So apply this to the first statement above. T of a would therefore, which is equal to limit n goes to infinity, I minus ia over nh bar times p n times, and this is nothing but e to the minus whatever is there here times the operator. So this is minus ia over h bar times p. Okay. So once I know the form of the generator, all I have to do is exponentiate the generator to get my finite translation. Simple enough?
Sir?
Questions? Yes,
Sir,
please.
sir, what happened if capital N is not infinity?
Capital N is not?
Infinity.
Okay.
I mean, here you are.
Capital N is something that we decide, right? So I decide how to do it. And it is not possible to just take 3 steps of epsilon and get to a finite translation, right? So that is one point. Any finite translation, by definition, I have always said that when I talk about an infinitesimal transformation, what is an infinitesimal transformation? The parameter of transformation is infinitesimal, right?
Yes.
So suppose if I'm talking about translation, then I'm taking an extremely small step epsilon. And what is this epsilon? Nobody tells me what this epsilon is. It's completely up to me. And I will say that this epsilon is 10 to the minus 100 and nobody can stop me. So which means to get to a finite translation, I have to bunch together a whole bunch of these infinitesimal transformation. How many? Well, mathematically, I have to take the limit n goes to infinity. Okay. So if I'm talking about rotations, this becomes an infinitesimal angle of rotation. So if I want to rotate by 15 degrees, I start with 10 to the minus 35 degrees. And then if I take the limit of n goes to infinity or into the 35 or whatever it is, you can always adjust it such that it is always n equal to infinity, gives you the finite translation.
Sir, but the only thing that I don't understand, let's say I have a square, okay. So if I take the rotation, it will convert into itself after 90-degree rotation, okay. The angle between them 0 to 90 degree, they are not accessible for me. So how I am going to take the small theta?
I don't understand the question. I'm sorry.
I mean, sir, if I have a cube, okay, I rotate 90 degree, that it will become cube. I mean, it has a symmetry. So 0 to 90 degree, because it has a 4-fold symmetry. So first I rotate 90 degree, then it will convert into itself. So how I am going to access that small theta, so that all the theta, if I sum all the theta, then it will give 90 degree.
So first of all, this has nothing to do with symmetry at all. See, this is how I would do finite translations, whether or not translation is a symmetry of the system. Okay, so these two are completely independent. See, you have some physical transformation that you do. Okay, either spatial transformation or something else, and then you ask, what is the way in which this transformation is realized in the Hilbert space? And the way this transformation is realized in the Hilbert space is by some unitary operator acting on the kets. That is the first statement. Now, if it transpires that this transformation is actually a symmetry of the system, then you claim that the Hamiltonian commutes the generator of these transformations, whatever these generators are. That is the statement of symmetry. Now, here I'm talking about finite translation. It has nothing to do with symmetry. Whether or not the translation is a symmetry, I can always think of a finite transformation as being put together by a whole bunch of infinitesimal transformations. So don't complicate this in your mind. So it's actually quite simple to understand. All I'm doing is I'm going from x is equal to 0 to x is equal to 5 in an infinitely many small steps. That is all I'm doing. Okay, regardless of whether I'm talking about transformation that is symmetry or not, as long as I'm doing a continuous transformation, I can always do this. There is no way I can do this for parity, for example, for reflection, right?
Yes.
What is reflection? X goes to minus x. I don't go to x goes to minus x in 15,000 steps, right? It happens like that in one fell swoop. Another example is charge conjugation. I convert an electron to a positron in one step. I don't do it in very many steps in which intermediately there are very many different kinds of particles, right? So I am, as long as you're not talking about a discrete transformation, for any continuous transformation, this is a legitimate approach. You just take an infinitesimally small transformation and then do this infinitesimally small transformation many times till you achieve your goal.
Okay, sir.
Okay. All right. Any other questions or comments?
Sir?
Yes.
Sir, you were saying that for a continuous transformation, going in terms of small steps is the legitimate way. But I have a doubt, like, is it the legitimate way or is it the only way to perform a transformation? Like,
so in quantum mechanics, see, there is nothing wrong with starting with this kind of operator, e to the minus I over h. Suppose if by some magic you already knew what this form of the operator is, then you would argue that you actually don't need to know about generators and things like that, right? So why do you even need to know about generators? Because if you want to do a very small transformation, you will just put a is equal to 10 to the minus 56 or whatever it is. But the point is, this will miss a lot of interesting physics, and I cannot impress upon you what this interesting physics is at this stage. You would have to trust me on this. So suppose if I know what the generators of transformation are, as I will show when we discuss angular momentum, you know a lot about the quantum mechanical system under consideration. Okay, so I will give you a slightly complicated answer to understand this aspect. So everything, so let me confine my attention to angular momentum because that is what we are going to do. So the question is, why do you need these generators, and why do you, is this the only way, and can we just guess the finite transformation? Suppose if I did not know anything about the generators, what will I stand to lose? I will stand to lose a whole deal, because as you would actually see, there is a difference between a finite translation or a finite transformation and infinitesimal transformation. That is very obvious. But the point is, it is just more than a whole bunch of infinitesimal operations giving you a finite transformation. The point is that there is a very beautiful connection between the mathematics of all these infinitesimal generators and the mathematics of a finite generator. Okay, so in very at this point abstract language, it's a connection between what is called the Lie algebra and the Lie group. So what is this? Everything you need to know about the generators, you know by simply looking at the commutation relations between the generators. Okay, so please remember in the last semester when we discussed orbital angular momentum, all we needed to know was the commutation relations between Lx, Ly, Lz, and L square. And once you knew that, you can actually solve a problem that is rotationally invariant. In this semester, we will take it forward even more, and then we will talk about, just by knowing the computation relations of the generators, how much you can know about the universe around us. Okay, you would actually be able to guess that there are things called spin half particles just by looking at the commutation relations of the angular momentum generators. Things that you would miss if you simply looked at finite transformations and had no idea about generators. So the Lie algebra of the angular momentum generators would give you what are called, so this is in the mathematical language called the representation theory. So what is representation theory? So suppose if I do kind of a transformation. So let us say that you have a whole bunch of MSc students in a class, right? Now, suppose if I give you a particular assignment or a homework, right? Now, let us say that there is 30 students in this class, and let us say they sort of group together because, people knew them from BSc days and things like that. So there is about 10 students who said, oh, let us all do it together, let us discuss. And there's another 5 students who said, oh, we are all from the same part of India, let us sit together and do this. And there are 7 other people who did the same thing. So the class sort of divides itself into very many smaller groups. What is the action? The action is the solving of an assignment problem. So now this solving of an assignment problem, which is an action that I do to the class, tells me something very interesting about the class. It tells me about how the class divides up and discusses the problem between themselves. So if you want to know how the class has approached this problem, all I need to do is look at the individual groups of students instead of looking at all the 30 students together. So I'll look at the 10 students together and see how they approach the problem. I'll look at the other 7 students and see how they approach the problem. The other 5, other 2, other 1, whatever it is. So I can look at all these individual smaller subsets of the class and understand how they solve the problem, right? So in essence, mathematically, what I'm doing is I'm trying to understand the action of the transformation by looking at the specific representations in the class. So these 10 students form one representation and they tell me how they approach the problem. This 5 students is another representation and they tell me how they approach the problem. So I can piece up the class into very many smaller segments and understand how the students are approaching the problem. So in physics language, this means that if you do a transformation, then all you're interested in really is trying to understand the irreducible representations of the group of transformations. Irreducible representation simply means that instead of looking at the entire set of particles or entire set of objects or whatever it is, you look at sort of smaller subsets and see how these guys talk to each other, and they don't talk to somebody in another subgroup, another set. Okay, there is a very, very clear way of doing this out mathematically, which we will demonstrate when I talk about angular momentum. And all this is made possible by looking at generators. It simplifies the problem by saying that the action of a transformation can be understood by simply looking at the irreducible representations of that particular group. And I'm using the word group here very loosely. All I mean is I'm looking at the specific irreducible representations of the algebra. So simply by looking at the irreducible representations of the algebra, I would be able to guess the different kinds of, for example, particles in the universe that don't talk to each other under a rotation. So suppose if I rotate, an electron doesn't become a vector boson. Okay, but how would I know this? I would know this only if I understand the mathematics of generators. That is a very long-winded answer, and maybe it doesn't make sense immediately, but if you wait patiently for a few more lectures, I'm sure I'll be able to impress upon you the importance of generators. So there is another question. Wouldn't also this P momentum being generator also give the idea that the system under considerations is under a constant potential? Not necessarily. So a constant potential is not the only thing that is translationally invariant. For example, I can have what is called a periodic potential. So this is something that is you will study it in your condensed matter physics course. So you can have this is a very bad drawing. Okay, my iPad obviously did not like it. So this is an example of a periodic potential, and this is an example of a translationally invariant potential. What does this mean? So suppose if the distance from the center of this guy to the center of this guy is A, then this potential has a very nice property that if I look at V of X, and if I move by an amount A, the value of the potential is exactly the same. So suppose if I'm here and I move by an amount A, the height of this hill is exactly the same as the height of the hill here. Okay, so this is an example of a non-translationally invariant potential. So this guy has no translation invariance. The first guy has a translation invariance. Okay, so a constant potential is obviously trivially translationally invariant, but you don't have only just constant potentials. You can also have periodic potentials. So in your condensed matter physics course, you would study what is called the conic penny model. And this also gives you a very beautiful theorem called Bloch's theorem that tells you that if you have an electron moving in a constant periodic potential like this, the electron necessarily has to have a wave function which has an e to the iqx part and a translationally invariant part. So the wave function of an electron moving in this would have some form like this. Okay, you can actually guess this by simply looking at the very simple one-dimensional quantum mechanics of this potential. So there is very beautiful things that come out, and ultimately we can move on to band theory and things like that. Any other questions or comments? Okay. So let us move on to rotation. So we have about 10 minutes. I'll just set up the problem and then we will continue our discussion next lecture. So let us start talking about rotations. Okay. Now, my initial discussion of rotations will differ slightly from Shankar's treatment. Even though the physics is exactly the same, and then once I start talking about generators, I'll move on to Shankar's language. The reason I'm not following it verbatim at this point is that there are certain things that are important that Shankar relegates to exercises, so I'll just simply do them out. That is all. So notice again before I begin that there's going to be a lot of indices, and things are going to look a little more tricky than the translation example. But whatever you do, again, notice that this is also a continuous transformation. So I'm going to write the infinitesimal transformation as something times a small parameter times some generator. Okay. Now, in the case of translation, this small parameter was some epsilon, this generator was p hat. But in the case of rotations, things are going to become slightly trickier, but the format is going to be exactly the same. And then I'm going to construct at the very end, but we have to first understand what these generators are, and to understand that, we will move on to understanding the representation of the Lie algebra. So hold on, and you might get a deeper appreciation of the power of this language. Okay. So let us start at the very beginning. Let us start at the basics. So what is a rotation? A rotation is a set of linear transformations that changes, for example, your vectors x goes to some r times a vector. R is a rotation operator in 3 dimensions. I'm not talking about Hilbert spaces now. This is just rotation in spatial x, y, z direction, right? Now, for the first 15-20 minutes of this, I'm not even going to confine my attention to 3 dimensions. We'll move on to 3 dimensions later. Space could be 15-dimensional. The vector will still transform like this, except this R would be a 15 by 15 matrix. That is all. Now, any transformation that does this is not a rotation. A rotation is something that leaves the scalar product of 2 vectors invariant, right? So x transpose y before and after rotation should be exactly the same, right? So this is a scalar product of 2 vectors. So what is this? This is x. This is going to get transformed to x transpose r transpose, and y is going to get transformed to r times y. And if the left-hand side and the right-hand side are to be the same, then we not obviously require that the transformation satisfy the property r transpose r is the identity operator. Okay. But there is another caveat to this. Not all operators that satisfy this are also rotation operators. Why? Well, let us take the determinant of both sides of this equation. Determinant of r transpose r equals determinant of the identity matrix. Determinant of the identity matrix is just 1. Okay. Now, determinant of A times B is determinant of A times determinant of B, and determinant of A transpose is determinant of A. So the left-hand side is just determinant of R square equals 1, which tells me that the determinant of this matrix, whatever it is that is rotating this coordinates, can be either plus or minus 1. Okay. So rotations are those subcategory of matrices for which the determinant is actually +1 and not -1. -1 corresponds to space inversion. Okay. So R has the property that determinant R is +1. These are the subclass of transformations that we call our rotation matrices in three dimensions or 5 dimensions or 27 dimensions. It doesn't matter. Okay. In terms of the mathematical language of groups, the set of R matrices form a group, because if you take two matrices that have unit determinant and multiply them together, that also gives you another matrix that has unit determinant, right? So these guys form a group, and this group is called SO3. S stands for special, O stands for orthogonal, and actually SON. S stands for special, O stands for orthogonal, N stands for the number of dimensions you are looking at. Special simply means that determinant of these matrices is 1. Orthogonal simply means that R transpose R is 1. And N refers to the number of spatial dimensions that you are talking about. Okay. So again, rotation is a transformation, just like any other transformation. It affects the Hilbert space of the quantum mechanical system. Again, differentiate between the physical space that you are actually doing the transformation in and how this transformation affects the Hilbert space of the quantum mechanical system. So rotation, just like the transformation induced an operator T that changed all the vectors in your Hilbert space, a rotation R induces on the Hilbert space of physical states a unitary transformation psi goes to some UR times psi. Okay, where this UI right now is a finite transformation. We will move on to infinitesimal transformations in just a second. Okay, now how does this U affect? So again, there is an active view and a passive view. I can also think of U as changing all the vectors in the physical Hilbert space, or I can think of U as changing all the operators in the physical Hilbert space. How does it change all the operators? And operator O becomes a new operator, which is U dagger R times O times UR. Right? This is your O prime. Okay. So suppose if you have a vector operator. So what is a vector operator? A vector operator is not just an operator that has three indices, V1, V2, V3, but a vector operator is the one that transforms under this induced unitary transformation on the Hilbert space as, so let us, okay, so vector operator is U dagger R, a component of this vector operator V. If this gets transformed, this becomes some other operator Vi. But if this operator is to be a vector operator, then V prime should be exactly the same as how the x's transform. So how do the x's transform under the rotation? X's transform as xi is just Rij xj, right? This is the index way of looking at it. X1, X2, X3, X4, X5, they transform as Rij times xj. It becomes any single component becomes a linear combination of the coordinates. For example, in 2 dimensions, x prime is x cos theta plus y sin theta. So it becomes a linear combination of the old coordinates. Just like that in quantum mechanics, if we have what is called a vector operator, then the way this vector operator behaves under rotations is that its components get mixed up under rotations exactly the same way as any vector in a normal space, 3 space directions would transform. So this Vi prime, I claim, should be just Rij Vj. If this operator agrees with this equation, then I call this particular operator as a vector operator. Similarly, I can also define a tensor operator, but better still, we'll actually derive the transformation property of a tensor operator. But today we are running short of time, so we will postpone this discussion to the next lecture, where I can give a self-contained lecture on how a vector operator transforms and how a tensor operator transforms. But for today, we will stop at this point, and I will ask if there is any questions.